Welcome back to Black Robot. In our last chapter, we saw the market trends and job opportunities in IoT and embedded systems. Now let's go deeper into the technical heart of all these systems, the microcontroller. This chapter is called Microcontroller Basics Architecture. Why microcontrollers? Here is a question for you. What do you think the motor in your washing machine or the display in your microwave? Who controls those? So think about that. The answer is microcontrollers. It's the heart of embedded systems, integrating CPU, memory, input output into one small chip. Because of this, microcontrollers are cost effective, compact, and efficient. That's why they are everywhere, from kitchen appliances to IoT devices. What is a microcontroller? Think of a microcontroller as a tiny computer inside a chip. It has CPU to process, memory to store, input output to connect to the outside world. It same goes for the TV as well. Think about that. When you control through your remote, is just switch into the application. When you click on that, particular video gets selected. How it happens? Okay, so unlike laptops that can do many tasks, microcontrollers are designed for a specific controller task. Example, if I will give you a microwave, microcontroller only manages cooking time, motor, and beeper, and remote control. And a smartwatch is also there. So what is the difference between microcontroller and microprocessor? Microcontroller is all in one chip that has CPU, RAM, ROM, input output on a single chip. That is also a low cost, low power. For example, Atmega 328 in Arduino, that is microcontroller. What is microprocessor? Microprocessors only have the CPU. It needs external memory and input output chips as well. It's more powerful but higher in cost, just like Intel i5. So microcontroller is like a Swiss army, right? Swiss army knife, everything built in. You will get everything on single thing. So while an MPU is like a high-end desktop computer that requires accessories. So role of microcontroller in IoT in embedded systems. So microcontrollers are everywhere in this world, in IoT, okay, in embedded systems. So they collect the data from sensors, process it in real time, it controls the actuators, and sometimes send the data to the cloud. So that's basically the IoT we have discussed previous as well about these things. Okay, so these controllers like ESP32, STM32 with the Wi-Fi board. So an IoT temperature sensor microcontroller read the data, process it, then sends it via Wi-Fi. Without microcontroller, IoT devices would simply not exist. So it's an internal architecture of the microcontroller. If you're seeing here, that typically having the component CPU, RAM, ROM, flash, GPIO ports, timers and counters, communication interfaces, ADC and DAC, interrupts, clock systems. We are seeing here timers is connected, on chip RAM is there, and on chip program memory is there. So interrupt control which is connected on chip memory and CPU and oscillator is connected with the CPU. So if you are on to this bus, there is a bus control, input output control, serial port is there. So this is whole package, we call it microcontroller. Okay, so each part has a specific job and together they make the system work. CPU. Well, what is CPU? I think you have studied about the computers, laptops, how CPU works. So that's the same thing CPU does. into the microcontroller. So the CPU is the brain of the microcontroller. So that's ALU basically cal- does the calculations. What controller unit does, it fetches and executes instructions. What register does, it stores small data instantly. For example, Arduino Uno uses a 8-bit CPU at Mega 328. It's small in size, but enough to run projects like blinking LED or sensor monitoring. Memory system. So memory we need to, when we are working on embedded microcontroller or IoT systems, we always have to keep in mind what is the capacity of microcontrollers. Okay, so there are three main types of memory: flash, ROM, that stores program code. It means that non-volatile. RAM, that's temporary data, that's volatile in nature. Okay, EEPROM, that's permanent storage or small data when you are going to keep it. That can be, 2 KB, 8 KB, 16 KB, like that. Okay, for example, Arduino is having 30 KB, 2 KB flash, 2 KB RAM, 1 KB EEPROM. So there comes the input output ports. Why we use it, right? To connect the sensor pins or accu- actuator pins with those ports. So GPIO is basically general purpose input output pins. Digital input output is basically we can use for on and off like switches, LEDs, and log pins is just like to get the continuous values from the sensors. So for example, Arduino reads an analog temperature sensor. It processes switches on a digital fan. Suppose you are having a range. If your temperature is going beyond 30 degree and you have got the data from the sensor that's 31 degree. So it will just on the temperature. It will just on the fan there. Okay, the fan will be on. So that's the work of process of these boards. You can make it according to your project. GPU is what makes MCUs, means MCU means here microcontrollers, interact with the real world. What is timers and counters? Timers generate delays or signals. Counters count external events. For example, a timer makes an LED blink every 1 second. Okay, so it means if you want to just on the LED after 10 seconds, you will use the timer here. There the timer will come to the picture, and just like PWM from timers, so that control motor speed or LED brightness. Okay, so without timers, real time control would not exist. So that's the use of timer. And counter is just counting the every steps. What are the external steps are happening into the real world. Serial communication interfaces into the microcontroller. So there are UART, SPI, I2C, CAN. UART is basically a simple serial. Okay, so and SPI is fast for displays and memory, and I2C is the two-wire multi-device. SPI is four-wire, and UART is also two-wire. CAN is basically we use for the automotive networks. So later in lectures we will learn more about in details, and you will get to know how these serial communication works with the controllers. Okay, so just like USB32 uses UART for debugging, I2C for sensors, and SPI for display. Okay, so when you are using the debugging, so you want to get the logs. So there, the RxTX receiver and transmitter pin is there. There you can use the UART method and get those logs for debugging. I2C to read the sensors. But in most of the cases, I'll give an example of RTC. RTC is I2C based. You can use it. The same is for SPI for display if you are using any board, right? So there you can use the SPI protocol. ADC and DAC, real world is analog and microcontroller, all the things read into the digital format. So we need ADC and DAC format. Analog to digital or digital to. Okay, so ADCs converts analog sensor value to digital, and DAC converts digital to analog signals. For example, ADC reads light sensor, adjusts LED brightness, and DAC outputs audio tone as an alert. So that's where DAC use it. Interrupts and exceptions. Interrupts is basically MCU gets a sudden call. Okay, it stops current task, handles urgent event, and then returns it. So basically, if two work is happening there, two task is happening, one you have given a priority one that is onto the priority. Okay, if any interrupt is happening, any event you have got it. Okay, the that first task will come first into the picture and notify to the customer, yes, this is running where. Okay, so that's kind of, you can tell, that is basically a accidental thing. Okay, if any accident is happening, so the car would get a hit crash message. Okay, so that task will hit it, and you will anybody will get it notification, yes, that crash somewhere has crashed with something else. Okay, so that's basically interrupts. So for example, a motion sensor interrupt wakes and a microcontroller from sleep. Okay, just now we have discussed. Okay, so this allows real time response, critical for IoT and automotive systems. So clock system, what is clock system here? Microcontroller need timing. Where there are two types, is having internal oscillator and external crystal. Internal oscillator is cheap and less precise. External crystal is accurate and stable. For example, Arduino Uno runs at 16 megahertz clock speed. The clock defines how fast instructions are executed. So this help in uh, execution of instructions. So microcontroller architectures, if you're seeing here, so these are the families basically, we can say. Okay, so in this architecture you will get common microcontroller 8051. Okay, so it's old but still used in education and traffic lights. AVR is there. Student projects, hobby IoT projects nowadays students are using. ARM Cortex-M, that is basically industry based IoT, automotive, drones, medical system, everywhere we are using nowadays. So STM32 basically used into the industrial robots, ESP32 in smart bulbs, TI MSP413 wearables. So what are the case studies are there? If workflow, if you are seeing sensor takes, use the ADC, then it processes your CPU and it is displayed. So MCU manages everything: reading, calculating, showing. So it is used in hospitals, wearables, weather, and stations. Okay, this is the first case study. You can use it as a digital thermometer there. How it process it, you can make it from yourself. Okay, so that's a digital. So where you can use it in hospitals, weather stations, and wearables. Second case study is smart home IoT node. So basically, PIR detects motion. That is basically an interrupt. Okay, then after that, microcontroller process those data and send via Wi-Fi. So in that case, cloud updates mobile application. So light or alarm will be on and off. So in that case, you can make it, temperature, humidity sensor, voice assistant integration. These kind of things you can use in smart home. This is the basis of smart homes. Nowadays, if you're seeing how smart home is happening, so you can add Alexa or Google Home with those controllers, and you will hello Alexa, on the bulb. So it will on the bulb. Turn off the fan, it will turn off the fan. This is how smart home is working nowadays. Automotive is, so one more case study. In that case, in cars, microcontroller handles safety critical systems, right? Just now we talked about the crash related thing, how it happens. That nowadays for engine controls, ABS, airbags, infotainment, everything. Okay. So for example, if you are pressing a brake there, so sensor will activate it, it will send the signal to the MCU controller, and ABS motor will just act it according to that. It means just it will stop the car, vehicle, any vehicle. So other tasks also it can give. Engine control is there, safety systems is there, infotainment is also there. So automotive issues are highly reliability ARM Cortex-M CPUs. So what we have just seen about how what is the you know architecture of the microcontroller, how microcontroller is the brain of embedded devices. So in an architecture we have studied just now CPU, memory, input output timers, ADC, DAC, interrupt clause. And also in those families we have seen comes 8051 AVR ARM Cortex M as well. So in case studies also we have studied thermometer. Okay, then after that automotive ECU and smart home IoT node and digital thermometer. This kind of case study we have seen how it processes it, right? We will go more in detail later lectures. So for now, if you are having any question, you can comment below. Okay, please do like, subscribe, and share these videos. Thanks everyone.